Okay, we'll pick up here. Major product. We did the first one in class now. Hydrohalogenation reaction. Addition of HI to an alkene. We have our mechanism. I don't think we did these two. Is this where we're kind of left off at? Yeah? Product here. The main question is where we're going to make cation. All these reactions have cation intermediates. Until we say it's done. We're going to make cation on left or right here. Is this thing on? Cation on left or right? Correct, because it would be a secondary cation. That would be better than making it primary. Secondary cation better. So when we attack the H+, okay, you can show this covalent or ionized. Either way works. The electron's going to break away from this carbon over here. So pull them away from that carbon and go attack, and we get boom, 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 boom. Make new bonds there, and we get that. Everybody there? Somebody pull the pin. Pull it over and make bond to H. Leaving this carbon without a bond, that's a plus charge. Here's the bond we just made. Right there. That's how you predict the outcome, the regiochemistry. And because the plus is there, guess what ends up there? Well, then this iodine, the next step, the fast step, you get that, yeah. Boom, 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 boom. And you get the iodine there. Okay? Iodine. There's a new H here. I tend to draw it in when we first put it there. It's still there, right? How many H's on this carbon? 3. I mean, on the original carbon?
2.
Only 2. There's a new one there. We added HI to the alkene. An electrophilic addition reaction. The iodine ends up on this carbon, mainly because that's where the cation was, because it's a secondary. Secondary is better than primary. So would you expect this reaction to be regioselective? Is the iodine going to end up in a certain region? A selective certain region? Yes, that carbon. It will not end up here as well, randomly. It's very selective. Reaction down here. Where are you going to form cation? Left or right of the alkene? Down here. Which side? It's going to be secondary either way. Let me ask you, do you think this reaction is going to be selective? Is it going to prefer one way? It's not going to be selective. You're going to get a mixture. And, I mean, you can think mechanistically, but you're going to get a mixture of... Really, okay, I'm going to draw it with the plus there first. This is your two possible cations. This is where it broke away from this carbon and made bond to H. There's a new H here. Okay, if you want to draw in the new H, sometimes it's helpful just to draw it in. The new H is here. Which way is going to be preferred? Yeah, they're both secondary. The system is not going to be selective. Iodine can add here. Okay, I'm just going to draw it like this. I'll get rid of the undrawn H because it looks a little peculiar there. Iodine adds here. Get rid of the undrawn H. You're going to get a mixture of those. There's not going to be any regioselectivity. The first two reactions are regioselective. The third one is not. You're going to get a mixture. There's just not a well-designed reaction. Questions?
So in this case, you would want us to draw both?
Yeah, you would, because, I mean, which one would you say is going to be favored? Typically, I ask you for, you always ask for, what's the major product? Up there, this is the major product. Now, you might get a little bit of the other one, but we're always going to predict major product. It's going to be selective for this one. How selective? Well, I mean, that's down here. Is this one going to be major, or is that one? I mean, it's going to be. Now, if you actually do it, I shouldn't say anymore. There's just no reason for selectivity down there. Mainly because there's no reason why secondary versus secondary. It's the same cation. Question?
Symmetry wouldn't have any effect on
I
the,
didn't hear you.
symmetry wouldn't have any effect on preference?
I wouldn't call it symmetry, but there could be some things that might affect it. For us, though, at the introductory level, just looking at cation. Secondary versus secondary, which is favored? Neither is favored. They're both going to be formed. That's the idea of regioselectivity. Regioselective. In the context of this reaction, these are called regioisomers. Because here the iodine bonded at this region, here it bonded at this region. Regioisomers are just a type of constitutional isomers, but you call it regioisomers in the context of this reaction. Okay, synthesis. Synthesis is where, well, I mean, when you do a reaction, you're doing synthesis. But when you talk about synthesis in organic classes, you're typically talking about making something, and you're saying, hey, synthesize this. So you're starting with the end product. And you're asked, okay, show a reaction that would give this. So we're going the opposite way here. Where up there, I just call that simple line reactions or predict the product. This is more predict or provide this starting material. So how would you make this alkyl bromide, 2-bromopentane? How would you make that? Well, at the end of organic 2, you may know a half a dozen ways to make that compound. Right now, you only know one way. You only know one reaction. We will build our toolbox as we go along. The only reaction you know is adding HX to an alkene. Well, you got an X here, you got a bromine, so you can add HBr to an alkene. That's all you know right now. So, what alkene do you want to use? Show the alkene. The question here is, do you want to have the alkene between carbon 1 and 2 or between carbon 2 and 3? Do we want to have that alkene or do we want to have... Now I'm going to draw this one as trans. You watched the nomenclature video. This could also be cis, stereogenic. Is that alkene stereogenic? No, it's not. You cannot have cis trans there. I'll draw that one as trans. Which one would you rather? Your mission is to make this in highest yield, always. React this with HBr, or react this with HBr? Which would you recommend if you were? Which one? Why do you like the bottom better?
Yeah.
Is it going to give that product selectively?
Oh,
No, we want
that's
you
at
at
the
the
top.
I'd rather have this one. This is not going to be, where are you going to make cation? On this 2 or 3 carbon?
Either one.
Either one. You're going to end up with, if you do it this way, you're going to end up with this, but you'll also end up with what? I'm not going to say plus here. This will give both of these. That's not going to be regioselective. What about up here? Is this going to be the major product up here?
Yes.
Yeah, you're going to make cation here. So this is the way that you would design the reaction as being a high-yielding, regioselective synthesis. Anytime you synthesize something, you want to have the best, the highest yielding. Okay? How would you synthesize that compound over there? What is that? 1-methyl, 1-chloro, 1-methyl cyclohexane? How would you synthesize it?
Put the
there's actually two different ways you can do it here. Both are going to be regioselective.
What you just said was put the double bond here, like that. Yes. And usually that's often forgotten about or not considered. Yeah. React this with what?
Well, it's HCl, right?
Where are we going to make cation? Top or bottom?
At the bottom.
Bottom, yeah.
You got your top and bottoms mixed up. Okay. Right, top, okay. We made cation at the top, that means the electrons broke away from the top, went and bonded to H, left that as a cation. Well, that's a primary cation, that's not a good cation. Instead, the electrons are going to break away from the bottom, yeah? And we're going to get the H bonded up top and the cation at the bottom. Okay? The electrons are going to go like this. And then, why? That's tertiary, right? Tertiary is your best cation. Then we can go back to, well, what's going on here? Since it's a better intermediate, the transition state leading to it's going to be lower. And so the energy is not going to go uphill if it doesn't have to. We went through that last time. But you could also have that alkene. Two different alkene starting materials. Where are you going to make cation, left or right?
Left.
Correct. And it will also get the same product. Two different ways to make the same product, both ways being regioselective, should be theoretically high-yielding regioselective reactions. Any other place to put the double bond?
The other side.
Okay. Could you put it on the other side? I mean that. So we have three ways to make it. Yes or no? This is the same compound. It's the same thing. Just like that and that is the same thing. If you name it, it's the same exact name. So, no, it's still, that's just a duplicate. It's only two ways. Two ways. Okay, questions? One down below, go ahead and get you thinking about this. Major product down below. Think about it. Think about it. We'll come back and revisit it. Possibly may involve considering resonance. I'm not sure. Resonance. Ultimately, what's going to drive the regiochemistry here? Stability of your intermediate. So really what this question is which cation is going to be most stable? Show both cations and consider which is most stable. Once you find the most stable cation, we'll then just add the bromine to that cation, and that's going to be your product. Okay, I think that's Roman numeral 1. Let's see where we're at. Lecture file. Looking at that definition, cation are species with empty p orbital. Mostly, I reckon an H plus doesn't have an empty p orbital. So I would maybe get rid of the p, make it more broad. That's, I don't really like that definition because an electrophile can also just be a partial positive. It doesn't have to have an empty orbital. You need to understand what an electrophile is, what a nucleophile is. I give you a couple of example definitions, but there are other definitions as well. Roman numeral 2, different reaction. Addition of water to give alcohols. Please remember on the previous page, we also have the outline shown as the scheme there. Okay? We just hit HX to give alkyl halides. Now we're going to add water to give alcohols. Okay? So no, we're always going through here. Okay, first off, an alkene does not react with pure water. Pure water is not electrophilic enough. The skin of an apple is largely made of alkenes. When it rains, do the alkenes in the skin of the apple react? No, they protect the inside. They protect it from water. They don't react with water. Okay? But the alkene will react with H+, which is what we reacted with when we did like HBr essentially. And H+ can be in the ionized form or it can be in the covalent, highly polarized form. So, but what we can do here is we can get an alkene to react with water, but we have to include H+. And the H+ is going to serve as a catalyst here. Now when you combine water and H+, you typically show it like that, right? So it may just be shown like that, H3O+. Now that's very generic. If you go to the stock room and say, hey, give me some H3O+, they're going to look at you kind of weird. What specific acids serve as H3O+? This typically means strong acid. Sulfuric, okay, the H+, sulfuric, phosphoric, or we can use HF. Note that we did not use HF for the hydrohalgenation, only HCl, Br, and I. These are typical acids that are used as catalysts in hydration. No, you don't want to use like HBr as your catalyst. Because if you use HBr, you'll end up doing a hydrobromination like we did on the other reaction. We'll say more. Mechanism. Okay, what you want to strive to do is find similarities in all these mechanisms. And in finding similarities, you also recognize the differences. Okay? But the similarities you don't have to learn over and over and over if you just learn it once. So, the alkene doesn't react with pure water. First off, what is this? Aqueous sulfuric. Well, isn't aqueous sulfuric aqueous acid? It's water with H+. So first, I'm trying to get you at, this may be shown in a variety of ways. Aqueous acid, that's what we're dealing with here. Water and acid. Okay, the sulfuric acid supplies the proton. We can show it ionized. The alkene attacks the H+, just like in the previous reaction. Where are we going to make cation, left or right? Left. Tertiary, correct? Just like the previous reaction. Here, though, we do not have a halogen that can attack. Instead, the nucleophile is the thing that likes a nucleus, and a nucleus is positively charged. So it likes positive charges. Here's a positive charge. This guy likes it. Why? Typically, nucleophiles have lone pairs. It's going to react. So these electrons, every time you move an arrow, what do we say? These electrons. These electrons attack H+. These electrons make bond to cation. That's going to give this, with this bond made. Now we're almost there. But we have to lose a proton from the original water. Well, here something takes it. if the conjugate base of sulfuric acid takes it, we can reform sulfuric acid. Now, this is just an acid-base reaction. Okay, let's explain this. Usually I want you to show full Lewis structures with everything. But I tend to sort of let you get away with this guy here, sort of the okay, this is this. And these electrons make bond to H. These electrons move on to the oxygen to become the second lone pair. It's just an acid-base reaction. Well, what does this give? We now have two lone pairs on the oxygen. And that's product. But what are we doing over here? This makes bond to H. This becomes H2SO4. And the H2SO4 was our catalyst. And here we did. We reformed it, which is definition of catalyst, right? It's reformed. And this is a typical hydration of an alkene because we added water to the alkene. But it wasn't pure water, and the alkene didn't react with water initially. It reacted with the H plus catalyst. How many intermediates in this mechanism? 2. Carbocation intermediate, and then this positively charged oxygen intermediate. 2 intermediates, right? Okay, questions here? Now, I typically will let you get away without showing this full here. And I usually just do something like this. It's a little bit sort of not as precise. But please know what's going on there. Hydration of alkenes is a common way to make alcohols. Here we used a H plus catalyst that was reformed. Note, some books may use water to take the proton. This is actually strictly more correct. That is, if water took the proton, we would get this plus what? We get our product plus what are we forming here? H3O plus. I thought that was super easy. H3O plus, right? Okay. Well, guess what? How does aqueous sulfuric acid actually exist? That's how aqueous sulfuric acid actually exists, right? Okay. So, there. Because we're talking about aqueous acid. How does sulfuric acid exist in water? It exists with this and HSO4 minus. Maybe even more ionized than that. I, though, actually like to reform the actual acid. So I will always do this. It's actually more correct to show water if you've got an aqueous acid. But I will always do this. This reaction can be reversed. That is, you can take an alcohol, react it with sulfuric acid or one of these acids, and go back to the alkene. That mechanism is covered a little bit later, mainly in Organic 2, beginning of Organic 2 when we cover alcohols. It's just a reverse. That is, if you look up top, every reaction can be reversed. That is, you can have an alcohol, you can protonate the oxygen using the acid. Then, the water can just leave. And that would be where it's serving as a leaving group. Okay? And then at this point, you can lose the H and the electrons can fall in. It can be all reversible. And at some degree, that's an equilibrium reaction. But for us, it's going one way or the other. But if you reverse it, you would call it a dehydration, because if you remove water, you're dehydrating the alcohol to make the alkene. Okay, predictive products. Do the first one there. Forgot to mention why choice of acids up there. Why choice of acids? The acid's important because right here. If we had used HBr, you would have had a Br minus floating around. Well, Br minus could add to cation. You're going to get like an alkyl bromide. Or a chlorine or something. These acids are used because the anion will never react with anything. Bisulfate, biphosphate, F minus. F minus will actually rarely act as a nucleophile. So the anions of these acids won't react, and the only thing that can react is water. That's the only nucleophile. And so you get the outcome you want. So choice of acid is important. Product down here. First one. Somebody got it? Can you name it? You just name the substituent as, for alcohols, there's a certain nomenclature, but you can also just name the OH as a hydroxy group. Someone name your product? Hydroxy is in what position? It's going to be at what? 1, 2, 3, 4, 5. Pentane. Hydroxy is at what position?
2.
Yeah, 2-hydroxypentane. Now, a better name for that would be 2-pentanol. But yeah, because where are we going to make cation? What is this reaction? The alkene reacts with what? H plus, right? This is H plus in water, but alkenes don't react with water. So all they can react is, it's H plus, and we're going to do the same old reaction, right? Boom, 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 boom. H on the end, plus here. What adds to the plus? The water. And you got to lose a proton so it doesn't get there directly. But after you lose the proton, we end up with OH there. And yeah, it's 2-hydroxypentane. Better known as 2-pentanol. Is that reaction going to be regioselective? Would you expect maybe 1-pentanol to also be formed? No, it should be regioselective. Regioselective hydration of the alkene to give the secondary alcohol. When you do primary secondary of alcohols, you're actually referring to the carbon it's bonded to. Okay? The O can always be only bonded to 1. This is called a secondary alcohol because the carbon it's bonded to is secondary. You'll see that later on. Okay, how about down here? Down here brings in the fact that you don't have to use water. You can use acid and some other oxygen nucleophile. This is some other oxygen nucleophile, and the acid comes from HF. HF is one of those acids where it just applies the H plus and the F minus won't do anything. Now, I want to keep it dry here. I'm using a dry acid. I don't want any water around. Can you predict product here? Well, just like water, alkene's not going to react with an alcohol. So we got acid. Okay? Where are we going to leave cation, left or right? On the tertiary carbon, right? So we got the H plus, F minus. This attacks like this, and we get the cation here. New H there, right? Electrons. Move away, leave this without a bond. We made the bond there. What's going to attack the cation? Will F minus attack it? No. Well, there's no water here. Yeah, this neutral oxygen. This attacks. But these electrons make bond. So now we can show it with those electrons now bonded. Here it is. Here's the oxygen. One lone pair is now bonded. There's one lone pair left. What else is left? An ethyl and an H. Because these electrons are now bonded. That's what the arrow means. Well, but there's a charge here because the oxygen is positive, so we need to show that also. And this is where the ethanol acted as a nucleophile and added to the cation. Okay. Well, that's a positively charged product. Typically, we want to go neutral. Can we go neutral? How did we go neutral up here? Something took an H from the oxygen. Well, it's the same thing down here. What do you want to take? Something's going to take the H from the oxygen. What can take it? Somebody said water?
Fluorine.
Oh. Okay. Yes. What if these electrons here take the H and these electrons stay behind? What do we get? O, ethyl, two lone pairs, plus what? What did we make in our HF? Huh, we reformed HF. So, what did it serve as in this reaction? Yeah, you see, we reformed it. It supplied the H plus, which is what the alkene will only react with. H plus ain't going to react with ethanol. But ultimately, what did we add to our alkene? Ethanol. Because if you look at the formula, this formula now has ethanol added to it. But it involved a catalyst in the process. It wasn't just adding ethanol. If the acid wasn't there, the alkene would not react with the ethanol. The catalyst has to help. Now, you're taught in Gen Chem the catalyst speed reactions up, I reckon. Well, I reckon it works. If you go from 0 to 10, you sped it up, right? But 0 is nothing. I mean, without it, you get nothing. Now you get a reaction. So it did speed it up, but for most organic, it's catalysts like make the reaction work more than just speeding it up. Now there are some reactions that may go slow without a catalyst, but most often it's got to have a catalyst just to work. Okay, so here we actually did not make an alcohol, did we? That's not an alcohol. What is this? I mean, that's an alkane, cycloalkane, but what is this here?
Ether.
Yeah, I think that was on the test, wasn't it? Ether? Was there an ether on the test? Okay. All right. Now, ether is actually Roman numeral 3. But what's the big difference between adding water and adding an alcohol? The only difference is you got an R group here. It's the same mechanism.
For the first
one that you drew, you put the hydrogen off of the second carbon on the ring. Does it, and then for the next thing you drew, you put it back on the first one. Does it matter?
I'll put, it's here. What do you mean I put it where?
I guess it's just, I'm confused as to why it's over there and not on the methyl group.
On the methyl.
Yeah, like,
No, the electrons, here's the alkene. They break away from this carbon, the one with the methyl, and go attack the H. Here, it's right here. They go attack. Now this carbon bonds to the H. And that one has no bond at all. It's a cation.
so then we just drop that guy.
Well, like I said, I usually draw it when I first put it on there, but it's here. How many H's on the original carbon? We asked this on day 1. Carbon makes 4 bonds. There's 1 H here.
Oh, so he just moves over to, okay.
But how many are here?
Yeah.
Now 2. That's because we got a new one. I just didn't draw it.
Okay.
I just didn't keep drawing it. I mean, I drew it here only to just reinforce the fact that it's new and we just added it
I
there.
got you. Yeah.
That's important because I have to make sure everybody understands me. You keep track of your H's. And that's my style. I just draw it once. But I realized, yeah, where did it go? No, it's still there. Okay, so that's actually Roman numeral 3, which is addition of alcohols. And I said it's analogous to number 2. Okay? And we can make ethers this way. Again, this reaction would be regioselective, right? Or would you expect to get the oxygen bonded over here just as likely? No, it's going to bond, you're going to get the tertiary cation. All right. Carbocation. Roman numeral 4. Carbocations, you heard it here first. We'll keep track of these statements. This one occurred at 10:45 on Thursday, right after the first test. Carbocations are prone to rearranging. Prone to rearranging. Let's look at this example. Take this alkene, we're going back to HX, HBr. This is a minor product. We actually get that as a major product. How? Let's look at this. Where are you going to make cation at? Top or bottom? Bottom. Well, let's go ahead and do this. H plus, Br minus. These electrons pull away from the bottom. I'm going to kind of hinge them up and then attack. Okay? They go attack, leaving the bottom one without a bond. So this gives that one may. Okay? Yeah? Top carbon now has a bond to H. The electron swung out may bond to H, leaving this as a cation. How do you think we get this, the minor product here? That's hopefully a duh question. The Br minus, right? Just like we did, okay, this acts as a nucleophile here, and that would give the minor product. But it's minor product here. What's going on? The major is with the bromine added here. All right, I'm going to erase this. Let's see what's going on here. First off, how many H's on this carbon? 1. Can I draw it in? Let's look over here. How many H's on this carbon here, which looks like the same carbon? It is. How many H's there? None. There's no H there. How many H's on this carbon? 1. How many on this one? Still 1. We didn't add 1 there. We added 1 here. It's only 1 there. It's 1 H. If there was 2, it wouldn't be a positive charge. And if it was 2, I would say, well, where did it come from? There's 1 there. Well, how many there, which looks like the same carbon? 2. Now 2 there. It looks like somehow an H went from here to here. Indeed, that's what happened. What?
Why?
Okay, you're ahead of me. Let me draw it. Let's see.
What happens here is you get a hydride shift. These electrons, actually, here's the pin. They break away from this carbon and move and bond over here. I'm going to show it by saying these electrons break away. I'm going to kind of pull them away and move them over here. Now, a lot of students will just try to show the H moving. No. Because anytime you use an arrow, what do you say in your mind? These electrons. If I'm saying these electrons, why would I say these electrons and do this? It looks like I'm moving an H. I would have to say this H. No. The electrons in the bond, the hand is the H, the finger is the bond. The electrons break away from this carbon and move over. We're going to move those over. We'll talk about this more, but first off, what does this give? If they just moved over. I'll keep that H drawn in. But now it moved over, it did this. And so now it's bonded there. And there's no H here anymore. So there's only 3 bonds. And so what do we want to show here? The cation is there now. The cation has rearranged by what moved over? The H nucleus moved over, but also the 2 electrons. So the H and the 2 electrons. H minus shift. What do you want to call H minus? What do you want no. What do you call Cl minus? Don't call it chlorine, you call it chloride. What do you want to call H minus? No, not halide. This is a halide. Hydride. It's called hydride shift. Okay? H minus is possible. We will see it not as common as H plus, but H minus is possible. And this is essentially, if we're talking about the H and the 2 electrons, it's kind of, okay? Now what's going on here? First off, let's put some more stuff up here. This is what type of cation? Secondary. What type of cation did we rearrange to? Tertiary. Does that seem reasonable? We rearranged to a more stable. So the system is starting to fall back downhill. Cations will rearrange to more stable cations like this. Hydride shift is the most common way. What's going on with the hydride shift? Let's see if we can illustrate here. I'm a hydrogen bonding to you. And you've got other groups bonded to you. You're a carbocation. Okay? Now, I don't have a lone pair, but these sigma electrons between the H and the C kind of, well, let me attract to you. I see this plus, and these electrons, they start moving. Physics. But they like, sorry, I'm going to go over here and bond. So they move over and leave you without the bond. That's kind of what's going on. They move over, leave you. Why? Because you're able to handle the positive better. You're more stable being positive. And the system became more, okay? Hydride shift. Yes, the sigma bond is shifting. Here we go. I only drew in H's that we've been working with. Yes, there's 2 H's here. I only drew 1 of them in. Yes, there's 3 on the end. Now how do we get the final product, the major product? Yeah, the BR just adds here. See it? Watch this going on. Boom. Remember emerald? What does he say? Not boom, but bam. Okay, bam, right there. There you go. The major product comes from the hydride shift, the carbocation rearrangement. How do you get some minor? Well, maybe the bromide attacks here before it can rearrange. Okay? Here's what we're always going to say. If it can rearrange, that's the major pathway. We have to predict the major product. Always rearrange if you can. Carbocations, rearrange if you can. We'll see more examples and talk about it more. It looks like we're about out of time. Please look below. Do mechanisms. Always do mechanisms. Mechanism is your math formula to getting the math problem right. Look ahead a little bit, including over here. THC. Anybody familiar with THC?
No.
The cannabis plant makes it from this reaction. See if you can provide a mechanism for that. We're looking ahead a little bit. Let's do. Okay. See some of you in lab this afternoon right here.